I could just explain, and then you could go from there. All right? Now this problem might look familiar because you may have been presented this in a college algebra class. So let's say that you own some manufacturing company, and you've been asked to take an 8.5 by 11 sheet of aluminum or something, some metal that's not cheap. All right, and what we want to do is take this and cut out square corners. Does this look familiar? Yeah. You're going to cut out these squares, and I didn't bring any scissors, so I'll have to use my fingers here. So these squares are all the same, all right? Each square, they're identical. I'm going to cut these out. And then I'm going to fold up the edges, or the sides, like this. Oh, I forgot one. It's origami class today. So I'm going to fold up these edges. And then I'm going to come through and maybe weld these edges together, and I'll have a container. And this container has a volume to it. So I could pour liquid into this or whatever. I could fill it. It has volume, right? And what I want you to do at your table as a group, the first question, because there are going to be several questions. The first question is, it's not even really a question. I want your group to just pick some arbitrary value for this cut. Maybe you decide that you want to cut this out 1 inch or ½ an inch or something like that. And then I want you to tell me what the volume of the resulting container is going to be. Does that make sense? Okay, so every group pick your own number for how much you want to cut out here, and then determine the volume of that. Make sense? Tell me before you, yes, this is an 8.5 by 11 inch sheet. It's 8.5 inches by 11 inches. And when you choose how much you're going to cut out, let me know, because I don't want the same group doing the same number. You're going to do 1, okay. Y'all decide anything? You're going to do 2? 1.5? ½ inch. Okay, there you go. So first question, everybody agree on the answer. I want to know the volume of the box that you're going to get when you cut out however many inches you're cutting out. Let's go. If you're coming in a little late, then please turn in your quiz. You don't have to cut it, but it's more for visual.
Wait, so we don't actually have to have it?
You don't have to, but I mean, if you want to, you can. Yes, okay, at least one person try and cut out the whatever it is. So, at least one person. When you get your volume, let me know. You have your volume? Okay. You got it?
Yeah, we got a 66.
Okay. How are y'all doing here? Getting there? Okay. Just right up there. It doesn't have to be perfect, like exactly 1 inch squares. I mean, I don't expect that you have a ruler, okay? So, do you have your thing yet, though? What did y'all do? Half inch or what? 1.5? 1.5? Okay. Try and cut your edges out and try and actually construct your box. I'm only going to give you all like another 2 minutes. Do you have your volume? Okay, just hang tight with it. Did y'all make a construction of your container? Yeah, I'd like to bring it up front. Is that okay? All right, so here we go. It's nice.
Is that better for you?
No, this guy didn't even measure it, so. Oh, this is nice. You didn't weld the edges, though.
I don't have a welder on me. I'm sorry. Fire hazard.
Is anyone still working on it, the volume? Did y'all get your volume? Yeah. Everyone has a volume? Do you have a little box yet? Okay, good. All right, you were 2, right? Can I see yours? Yep, I'm going to take it up here. Who else has their box ready? Anyone else? We had, someone did half inch, right? You did half, you regret that now, right? Now that you're trying to. 1 inch. Okay, who else? All right, you've got yours. You're 1.1.5, right?
Yeah, looks more like 1 though.
It's close. Good enough. And then where's my half inch?
Oh, hers is the one. I was just terrible.
Yeah, no, that's fine. Okay, good. Perfect. All right, do you have your volume? Okay, everyone, you ready? We have 5 samples up here. All right, this was half inch cut out, folded up. This was, well, whatever. Okay, 1 inch, 1.5, doesn't matter. These are pretty close to each other. This was 2, all right? And I did 3. All right, so you can see these are all very different looking things. All right, so what do you think in terms of the volume? Should we all get the same answer for the volume? No. You don't think so? Okay, usually some people will think the volume should stay the same, but it actually is going to change. So this was the half inch group. What did you get for the volume for half inch? 37.5? This is volume and this is the cut, okay? And then for the 1 inch, what did you all get? 58.5. And then for 1.5? 66. How about for 2 inches? 63. And then for 3, I got 37.5. So all you had to do, like for example, for the 2-inch group, they cut out 2, 2, 2, 2. So when they folded up the sides, they got this shape, right? And this distance from here to here is this distance, right? So you just took the 8.5 and you subtracted 2 twice. Yes? That's what everyone did for theirs? You took the 8.5, subtracted whatever your cut was, but you had to double that because it was off each end, right? Okay, and then you took the 11, so this would have been 8.5 minus 2 times 2, and then this side would have been 11 minus 2 times 2, and then what would this height have been? Whatever the cut was, so 2, right? Is everyone following this? All right, so it's obvious that we're going to get different volumes depending on the cut. So what do you think the next question is?
What's the most efficient?
What's the best cut to give you the most volume?
Close to 1.5.
1.5 is the best out of those, right? But does that mean it's the best? We don't know.
1.5 and 2.
It could be between 1.5 and 2. It might be between 1 and 1.5. Who knows? Yeah. Okay, go ahead. Figure out what it is. And this is not a matter of guessing. This has to do with finding the global maximum of a continuous function on a closed interval. Can you come up with a function? I'm giving you a big hint here. Can you come up with a function that represents that volume? What's the variable? What's the thing that's changing? Like for each group, what was the variable? The cut. So don't call this cut anything specific. Call it X, let's say. And see if you might be able to come up with a formula for the volume. So go ahead. When you have a formula, when your group has a formula, let me know, raise your hand, I'll come by and take a look at it. Use the same piece of paper, 8.5 by 11. Okay? Think you have a volume function? Is that a times or an x?
Times.
Those are times.
Okay.
Because that's horrible convention.
Yeah, that's why he put
Okay.
those in parentheses.
All right. Everybody agree?
Sure.
Are you just being agreeable, or
I mean,
do you understand it?
well, it makes sense. I mean,
Okay.
you're just subtracting the x variable is
Given
well,
that X is the cut.
but
Mhm.
that's only going to be accurate if,
8.5 by 11.
With 8.5.
Yes, I agree with that. Okay, so let's stick with this 8.5 by 11 sheet and now find the max of that. So yeah. So see if you can figure. Well, that'd be kind of cheating. Try and do it. Yes, we could. You could do that to verify. Y'all have anything yet?
No.
No? All right, I'm going to let y'all keep working. Do y'all have any formulas yet?
Oh, yeah.
Yes? Okay. Does everyone understand that and agree with that? Yes?
Oh, yeah, yeah, done.
So all you're doing is you're doing the same computations that you did up there, just replacing the x, the 2 with x, right? Just use parentheses. You got to wrap the 8.5 minus, wrap that, and then wrap that. There you go. Okay, so I'm going to, yes. Closed interval method. You need to figure out what the closed interval is first. Okay, that's good. Does everyone understand this?
Yeah.
Yes? No. So now you're going to use the method from last class. You're going to try and find the maximum of that function on a closed interval, but you'll have to figure out what the interval is. So what's the domain? What's the smallest x you could have, and what's the biggest x you could have?
1 to 1.5.
Go back to this sheet of paper. Y'all think about it. Y'all think about it. What's the biggest cut you could make? What's the smallest cut you could make? Formula yet? No?
The domain would be 1 and 2.
Well, that's going to be
Between 1 and 2.
number. So now we need to.
How about the function? Did y'all come up with the function yet?
It'd be like,
You've got the function there.
it'd be like y
Function
equals.
of phi?
Are we supposed to simplify it?
Well, that's going to be up to you, but we need to all make sure you understand where that's coming from.
Yeah.
Yes, you're all okay with that? Okay, so that is a continuous function. You need a closed interval. You need to figure out what's the domain, what's the smallest x, what's the biggest x that you could have for that. And you have to look at it in terms of you're actually going to cut out, like what's the smallest cut you can make, what's the biggest cut you can make.
So it's actually product.
Hey, did y'all figure out the domain? Like, because to use this, you have to have a closed interval. Have you figured out what the closed interval is?
That's what I'm working on, but this thing is way too complicated.
Would it be our 1/2 and 3?
What is x? What is x? The cut. What's the smallest cut you could have?
Are we going off of that?
No, you're not using, that was just to get us to understand that depending on the cut, we get different answers.
So I guess the base could be at like.
Well, y'all figure out. What's the smallest cut you could have? What's the biggest cut you could have? Y'all have a domain? What about 1/2? We used 1/2. That worked. Right?
To do all of them?
Mm-hmm.
Because I thought it was just like, we didn't know where the maximum was.
Oh yeah, no. Okay, yes, I see what you're saying. But let's act like we didn't know this. We know that it's somewhere in here. But in terms of using the theory of this section, we need a smallest value for x and a biggest. So what's the smallest? What's the smallest cut you could possibly make? I could go 1/4.
So like 0.00.
I could go 0.00001. 0 would be the smallest. And then you wouldn't even have a container, right? But that'd be the absolute smallest you could have. Now what's the biggest? I'll let y'all think about that. Do y'all have an interval yet?
Because I didn't want to wait.
Is that what we did for that one? So you good?
Do y'all have a domain?
I think we do. I think it's
0.
8.5.
Close. 0's right. But 8.5, if I were to come in here right now, what would happen if I try and cut 8.5 out of this? I mean, I still want to cut a square out. Okay? If I try and do 8.5
So it'd be divided by 2.
halfway, exactly.
So 8.5.
So you're going to cut this whole square, this out, right, halfway through.
4.25.
Yeah.
Mostly probably do 4. It'd be 0 to 4. With the arrow and
What's going on over here? Interval? What's the smallest x that you could have? 0. What's the biggest? If I tell you have to cut, if you have to cut a square out of that, the most you could go would be half of the shortest side. 8.5, divide that by 4.25. Okay, so that's your interval. Now you gotta do the calculus.
How do you find the derivative?
I don't know. How are you going to find the derivative of that?
I was going to distribute and then.
I like that idea. Like just multiply it all out first. That's probably going to be the cleanest way. If not, you're going to be doing a triple product rule.
Yeah.
Yeah. Did y'all get your interval, your domain? 0, yes. Okay, now closed intervals. Has to be closed, meaning that you can let it be 0. Then you wouldn't have a container. I realize that, but that would be the smallest, and then the biggest would be 4.25. And then for your derivative, I don't recommend trying product rule here. I recommend you multiply that all through first.
What if you just distribute the x?
That's what I mean. Distribute the x and then multiply, just expand it all out first. You're gonna get a nice little polynomial, and then you can just derivative clean.
So once you find out those
Are y'all trying to do a triple product rule or no?
We are. Should we not?
You are? Well, you can.
I was like,
Is that wrong?
No, it's not wrong, as long as you do it right. But look at the original function. Where is it? 11, yes. If I asked you to multiply the first 2 together, could you?
Yes.
Right, you just do like a FOIL.
Yeah.
And then if you multiply by x, you just throw an x through to everything. Wouldn't that be a nice clean polynomial function?
It would.
And wouldn't it be easier to differentiate that? Do you understand?
Yeah, I do.
Okay.
we're all set.
But it's cleaner. It's cleaner, that's all. I mean, you could do the product, but it would just be kind of a mess. So what are y'all working on? Did you get the derivative?
Yeah, I'm typing it right now.
Oh, you expanded it out. Okay, good. All right.
For the critical numbers, do we have to put the intervals in there too?
Yes.
To make sure they're like
Yep.
lower or higher also, right?
That's right. So you get your critical numbers, so you set the derivative equal to 0, and then you plug those answers into the original function, and then you also plug the endpoints in.
Okay.
So 0 and 4.25 or whatever.
So there's gonna be
Did you all finish expanding it?
yeah,
Yes.
and then you just take
And then the derivative of that. You follow? Yes, it's Monday, I understand. Y'all get a derivative yet? Y'all expanded it out? And then derivative, and then you set that derivative to 0, right? That's how you find your critical numbers? It's a quadratic, so you should be able to figure it out.
Oh, yeah.
Did y'all get that polynomial to start? Everyone got that? Okay. Yeah. Did you do it?
No.
Okay, you need to do it. Work it out. Take it the whole way.
So that's our, but we have to also. Let's get that. I already did it. Is it 4 bunches? Oh, you said 2.45? Yes, we can all grab it. We have to do that. Well, you're gonna hear about math when you get you the same data problem on the test. Yes, I know you're doing that.
How are we doing? Did everyone take the derivative and set it equal to 0?
Yes.
It's a quadratic. You have to use quadratic formula. I think that we've gotten to the point where we can just talk this through. All right. So let's recap this real quick and make sure I did all my math right. First of all, you all came up with the formula. Okay? Everyone was okay with that, right? And then we realized, okay, if we can somehow represent the volume as a function of x, then if this is a continuous function on a closed interval, you can find the max and min. So we expand it all out because we realized that doing a product rule would be tedious, right? So we expand it out, we get a nice polynomial function, we take its derivative. When we take its derivative, collect like terms, sorry. This is our polynomial. We establish a closed interval. The smallest cut you can make is 0. The biggest cut would be cutting halfway through the smallest side of the paper. So 4.25. Once you have that, you take the derivative. Here it is. Then you set the derivative equal to 0. When you set the derivative equal to 0, it's a quadratic, right? So we use quadratic formula. And I trust that you can all do a quadratic formula on a quadratic, right? So take this through, you get 2 answers. One of these doesn't live in your interval, right? 4.91 doesn't live in here. Which means 1.585 does. So you now take your 2 endpoints, and your critical number, and you plug them into the original function, which is this up here. By the way, did we have the other type of critical number here? Remember, to find critical number, you set the derivative to 0, and then you also look at where the derivative doesn't exist. But the derivative is a polynomial function. It's always defined. It's nice. It behaves well. So we don't have to consider that. So there it is, our max. 66.148 and some change on the end of that. I rounded it.
And that's the maximum volume.
That's the most you'll ever get. Can't do any better than that. Ever. Make sense?
That's by cutting off that much.
And you'll have to cut 1.585 inches out of each corner to make that happen. Now, this may not seem like a big deal, but this is the type of problem that can actually make or break a business. You know, you have, let's say you have to manufacture, 500,000 of these containers. Each of these sheets cost you money, right? And if you just go in there and say, yeah, just cut 2 and 2 and who cares? Everything here, right? We're throwing this away. This is money down the drain right here. We want to cut off the correct amount so that we can get the most volume out of this and we're wasting as little as possible. You could just kind of take a guess at it, or you could mathematically find your optimum solution, the best solution for you. Understand? Okay. I hope I made my point. Everybody in your group, let's say this table here, start a piece of paper, write your name. Everyone in your group, pass it to the next group, pass it to the next group, pass that around and give it to me. All right, I thought today what I would do is just start with an application so you can see, just how you could use this. But what we need to do now is we need to continue this with more complicated functions. All I've shown you up to this point are polynomials, and derivatives of polynomials are relatively easy, would you agree? Yeah? All right, so what I'm going to do now is pick up, we're going to still be in 4.1. Were there any questions? Did anyone try any of the homework and have any issues that they wanted me to address? Okay. All right, so let's try this. Let's do f of x equals x minus 1 cubed. And I want to look at the interval -1, 2. By the way, the problem we just did is kind of just giving you a sneak peek into, I'm sorry, I was sick all at the end of last week. I wasn't feeling good, so I'm just getting over something. That problem that I just showed you is leading you into what is called optimization problems, which remember I told you we're going to do some word problems later on. That's kind of an example of a very mild word problem, what we just did. So you can kind of see how we can incorporate the techniques of this section into word problems. Let's just focus now on doing some harder functions. So look at that one. Want to find the global maximum and global minimum of that function on that closed interval. So is it a continuous function on a closed interval? Yes. Is this continuous? How do you know that's continuous? What type of function is that? X minus 1 cubed. It is cubed, yes. But I could have sine cubed, then it wouldn't be cubic. It's a polynomial. If you multiply that out, x minus 1 times x minus 1 times x minus 1. Is my microphone on? Yeah. Okay. If you multiply that out, right, over and over 3 times and expanded it, you would have a polynomial. So it is continuous everywhere. So we're good to go. So first step, I'll just take the derivative. And for this one, I would use, what would you use? Chain rule, right? Drop the 3 out. 3 x minus 1 squared, and then times the derivative, what's inside? Which is just 1, so we're done. Right? That's it. All right, now let's set it equal to 0. When is that derivative equal to 0? 3 times x minus 1 squared equals 0. Thank you. Everybody is signed that was here? Okay, thank you. All right. How about solving that? You want to multiply it out? Like expand it? You could do that. How about divide by 3, both sides? We could do that? 0 divided by 3 is 0. Can't do it the other way. Can't divide 3 by 0. X minus 1 squared equals 0. Now I agree you could expand that out. But you could also take the square root on both sides right now. Right? Could? You still get 0, right? Square root of 0 is still 0. So x is 1. All right. Now, we're supposed to check, is this number in this interval? Yes, so we're going to keep it, right? If it wasn't there, we'd throw it out. We also need to look, is the derivative ever undefined, or does the derivative ever not exist? Well, the derivative is again a polynomial, which is well behaved. So this is not going to apply. So we only have one critical number, so we're going to plug in, what, the two endpoints. And this really, again, doesn't matter what order you put these in. All we're doing is comparing them. I think f of -1, what's that? If I plug in -1 in here, -1 minus 1 is -2. -2 cubed? -8. Okay. Let's plug in 2. 2 minus 1, 1. 1 cubed, 1. And then plug in 1. 0. What do we have? Okay, our global minimum, I'm just going to put min, even though we know it's a global min. The min is here, right? And this is our max. Yeah, we haven't really looked at that, though. That's what the next section is going to involve, is finding locals. This is just good for finding global on this interval. Okay? All right, let's do something more difficult. I think it's time, don't you? X to the 4/5 times x minus 4 squared. And the interval here, ooh, they didn't give us one. Is that a continuous function? Okay, this right here is a polynomial, this piece right here, right? Okay, x to the 4/5, just to remind you, means the 5th root of x to the 4th. That's what that means. And are you ever going to have any issues plugging any numbers into this? Can you take the 5th root of any number? Yes. Okay, you can't take this. You can't take the square root of a negative, right? Can't take the 4th root of a negative. Can't take an even root of any negative. So if we ever have an even root out here, we have to be concerned. But it's an odd root, that's okay. X to the 4th power, that should be a positive number. So this is all good. So this is well behaved. This is well behaved. Everything together should be nice and continuous. We're good. So take our derivative. I'll put it over here. The derivative of this function. Now, I heard something. Maybe I'll put the derivative over here. I need more room. How do you want me to take that derivative? Product rule and chain rule. Right, so our product is right here. Hey, could you distribute this through? Can you just right now distribute the x to the 4/5, or yeah, 4/5 through? No, because that squared would have to happen first. I don't feel like squaring that and then distributing, or do I? No? Okay, you don't want to? All right, let's just then do our product rule followed by some chains going to be in there. So derivative of the first function right here is 4/5 x to the negative 1/5 times the second function, x minus 4 squared, plus derivative of this one, 2 times x minus 4 to the first power. That's chain rule, right? 2 has to drop down. This to the first power times derivative of what's inside. 1. I don't need to write it. Finish off product rule. Okay, that looks bad. Now that's what we refer to as the raw derivative in the past. And I said you want to get into a habit of trying to match the back of the book's answer, because at some point we're going to be setting this equal to 0. All right, and that's what we have to do now. So let me try and clean this up. All right, I'm going to try and clean this up a little bit right now before I try and set it to 0. Just tell me if you agree or disagree with this. Yeah, that's the same thing, right? Okay, I just dropped the x to the negative 1/5 down. Now, do you remember last class I told you that when you set a fraction equal to 0, I did say this, right? Tell me if I didn't. The only time whenever you set a fraction equal to 0, you only have to set the top equal to 0? I didn't say that? All right, well, I'll state it now. We're going to have to set this equal to 0, aren't we? And that looks pretty bad. So when we set, anytime you set a fraction equal to 0, you only have to look at the numerator. Think about this. If you want to know when a fraction is 0, couldn't you always multiply both sides by b? And these b's would cancel. And over here, 0 times b is still 0, and you get a is 0. So I've just turned a problem that used to say a over b equals 0 into a equals 0. And you could do that every single time. So when I look at this right now, I see I have a fraction, right? Which is just part of this whole thing. I'm going to want to set that equal to 0. So what I'm going to try and do is turn this into one big fraction first. All right? One big fraction. So I need a what to put those together? Common denominator. So imagine that this is over 1 equals. All right, so what am I going to need to make appear in the denominator on the second fraction? 5x to the 1/5. I have to introduce that down here and on the top, right? That's what I need to get a common denominator? All right, so let's read off what's the new numerator going to be? This right here, right? This, okay. And then I have plus. Now take a look at this other numerator. It's actually not as bad as it looks. How about the 2 times the 5? 10? How about x to the 4/5 times x to the 1/5? Add the exponents.
So it'd be 1.
X to the 5/5, which is 1, which is x. See that? And then we still have what up there? X minus 4. All of this over 5x to the 1/5. Got it? Okay. And no questions. There's my derivative right here. I'll box it. That's f prime of x equals that. Now let's find our critical numbers. I'm going to set the derivative equal to 0. Now, like I just said, the only time a fraction can be equal to 0 is if the top is equal to 0, right? So let me just look at the top and set that equal to 0. And now you have the pleasure of solving that. You could expand it out, and it would be a quadratic, right, if you did that?
You wouldn't have to?
Mm-mm. You don't have to, no.
Yeah, you factor out an x minus 4.
Does everyone see an x minus 4 in common in both of those? Also a 2. There's a 2 here. There's a 2 in this. There's an x minus 4 here and an x minus 4 here. So I'm going to pull a 2 times x minus 4 out. I don't need to use brackets. I'm just using those to kind of stress that I'm pulling this out of both of these terms here. So what would still be left in that the first term there? What's still in there? X minus 4 and a 2 in front of it. Right? So if I did this times this, right? Multiply this times this, I'd get back that. And then what's left here for this other one? 5x plus 5x. Now inside that bracket, what does that turn into? 7x minus 8. So you get 2x minus 4, and then you said 7x minus 8 equals 0, right?
Now you just set all those.
Set each of those equal to 0. Any questions on what happened here? Distribute the 2 through 2x minus 8, add 5x, that's 7x minus 8. No? We're good? Okay, so set each of those equal to 0. You can ignore the 2, right? 2 is never going to be equal to 0. X is equal to 4. And 8/7. Yeah, check these, make sure they live in here. Do they live in here? Yeah, they both do, right? 4 is in there. 8/7 is a little bigger than 1. That lives in there. So those are both good to go, aren't they? Okay, so I have 2 critical numbers. What about the derivative being undefined or not existing?
They both work. You said earlier that they behaved well. So.
I said the original function behaved well. Does my derivative behave well?
Yeah, because it's polynomial.
Well, no, it doesn't because 2 can.
X can't be 0. What if x is 0? Get division by 0, don't I?
And then it's undefined.
And that's undefined. This is the first time this has happened, right? Now, everything else is okay. Like up top, that's a polynomial. This is all great. Do y'all see this? Up here is a polynomial, down here is a polynomial. Individually, they're fine. But this could be 0, and that could create division by 0, so that's a problem. So x can't be 0, right? So 0 is a critical number. It is a critical number because it causes this to not know what to do. That means we have a couple of things that could be happening here at 0. We could have, think about this carefully. Is our original function defined at 0? Was 0 in here? Didn't we say this was fine everywhere in here? You can plug 0 into that. So is our original function defined at 0?
Yes.
Yes. So we should have a dot somewhere, right? On this graph. It's not an asymptote. But the derivative is undefined there. could be a corner, could be a cusp, could be a vertical tangent. That's what could be happening there. Very good. All right, now what?
Now you have to,
You got to plug these three values into the original function along with the two endpoints. So I have 5 points to test. The biggest answer I get is going to be my max. The smallest is going to be the min. Here we go. So let me do it this way. F of -1, F of 5. Take care of my endpoints first. F of 4, F of 8/7, F of 0. All right, let's go through this. -1. -1 right here. What's -1 to the 4/5? That's what it is, right? -1 to the 4/5 is this. It's what we just said a second ago. It's -1 to the 4th. -1 to the 4th. 1. 5th root of 1. 1. Okay, so that's 1. When we plug in -1 right here, that's a 1. When we plug in 1 here, 1 minus 4, -3 squared. 0. What? -3 squared. 9. Okay, 1 times 9, right? 1 times 9. 9. Are y'all all right?
I feel like the calculator says negative. Yeah, it says -1 because x to the 4/5 is plugging.
Did you put parenthesis, -1, close parenthesis, raised to the parenthesis?
And it answers was
Let me see. No, you didn't put your -1 in parentheses.
Why? Where's the negative one?
domain error when I do
What negative one are you? Oh.
That's how you have to type that in.
yeah, it could be a domain error.
If you type it this way, what it does is it ignores the negative. It looks at that as being It actually looks at that as being -1 times 1. I know it's weird, but
Right.
that's.
So how would you type that original equation into just that y equals?
I wouldn't, because I don't need my calculator.
How could you?
You also have like a doctorate degree in pure mathematics.
Well, no, I don't want you to become dependent on that.
I'm using
No,
it
but
to
I also
speed
don't
things
want to
up.
second guess.
Yes, but are you doing the math?
Well, yeah, I got.
Look, I don't mind you using the calculator, but I'm not going to teach you how to use it. I know. All right, so here we go. 5 goes in there. I won't teach you during class. If you want to know after class, I'll be happy to share. Okay, 5 goes in here. Oh, crap. Okay, how about here? 5 minus 4. Let's do that one. 1 squared? 1, right? Okay, but I still need to put 5 right into this. So can I just write this for now? Can I write 5 to the 4th, 5th root? It's a pretty big number, isn't it? Or no? Maybe not. Because you're doing a 5th root, it's going to get smaller. So who cares? Let's just leave it like that for now. How about 4? 4. This is an easy one. 4 in here? 0. The rest doesn't matter. How about 0? Is that one easy? 0 in here? 0 to any power 0. Yes?
What, you said the answer for the first one is 9, right?
Yes?
How do you?
Oh, wait.
1 minus
Why didn't, yeah, sorry, yes, thank you. I'm glad you pointed that out. My mistake. -1 here, we said turned out to be 1, right? Yes? -1 minus 4 is -5. For some reason I put 1, I think because we were talking 1 too much. -1 minus 4 is -5. -5 squared is 25. Thank you for pointing that out. That's probably going to make a difference. Everyone see that? All right, 8/7. I'm going to need my calculator for this. What's that?
Now you're reading.
I don't need my graphing calculator. I need just a calculator.
We can't use our phones during class. So.
I could use my 4 function. Nah, I don't know. My scientific calculator.
You have a 4-function calculator if you have a graphing calculator.
That's true. All right, so I'm plugging in 8/7. I did 8 divided by 7, and then I'm going to raise it to the 4/5. So raise this to the 4. I get 1.11274. I'm rounding. That's what I get when I plug 8/7 in right here. And then I'm going to do 8/7 minus 4. So 8/7 minus 4, and then I'm going to square that answer. So here I get 8.163. And you know what? I don't even care anymore. Because this is about 8. This is about 1. That's not going to be bigger than 25, right? So this is definitely not going to be the max. Agreed? Like this is maybe the potential to be the max. Let's go ahead and do this 5 to the 4/5 also. Yep, 3.62. And that's it. So, what do we got going on here? What's the global maximum? 25. Where does it happen? At -1, which is one of the endpoints, right? What's the global minimum? 0. And it actually happens at 2 different places, right? It happens at 4 and at 0, which are actually inside this interval. You with me? I think we should graph that one, just to take a look. But I know how to type it in. Oh. And my interval was -1 to 5, right? Did that get -1 to 5? No, it's -1. There's a problem with there's an actual problem with the computer itself. It's having trouble with that. So let me just change something in here. X to the 4th raised to the 1/5. There we go. Okay, that's hard to see this. I'm going to have to adjust one more thing. There we go. Oh, I'll erase all that stuff for you. What were we expecting at the critical point of 0? What were we expecting? Something weird, right? A critical number? A cusp or something? We got it too. So here's our function. At -1, it's up at 25. It comes down. Ah, boom, you've got a little cusp there, or a corner. There's your derivative is undefined. Derivative is undefined. Function is defined, right? Comes up. We have, looks like something's happening in here. Is that at 1? No, that's at 8/7, everyone. That's at 8/7. Okay? It's going to turn out that would have been a local maximum, but we're not talking about that yet. Comes up, something interesting happened there. Comes down, here we got our minimum occurred twice, right? 2 places. And then this 5, nothing really, right? It didn't contribute. Understand? All right. So as you could see there, the algebra in that one was a little more challenging. Let's do something else.